why don't we just go ahead and get started, and I'll breeze through this conversation. David, have you watched it on the YouTube?
I have, yes.
Oh, okay. So we've got three people, all of whom have seen this presentation before. So what I need to do is to emphasize the parts that maybe I didn't emphasize properly on the video, and we'll breeze through this, and that will also help us be more efficient in having our conversation when we get to having a conversation at the end of the presentation. So I'm going to just share my screen, and we're going to go through these slides at the rate we can go through them. And if we clear that, does everyone see a slide? Okay. Okay, so the topic is, when will my computer have common sense? And I've been working on this for years and years because I've always been frustrated with what my computer can't do. And as a developer, I'm more frustrated than most people with things where the developers obviously cut corners and we're just too lazy to solve the problem properly, and you end up in these loops of problems. And so I'm much more easily frustrated than most, but I see now that there's light at the end of the tunnel. So as we talk about adding common sense to artificial intelligence, this is, as we were saying, was a kind of a complicated process, and rather just standing up and saying, well, it's going to be 5 years or 10 years, or a lot of people say never, I'm going to talk you through my line of thinking and the things that you need to do to be able to get common sense into a computer. And then we'll be talking about what the current state of the art is in AI and how your mind is different from AI. And I'll here bring up three important issues that I think are sufficient for common sense. That's my hypothesis. I think they're pretty clearly necessary for common sense, but whether they prove to be sufficient for common sense is not the key issue at the moment, because when we have these three things added to common sense, we will have made a quantum leap towards a better AI system, and we will have learned what it is are the next steps that we will have to take. So the question then is just, how big a deal is it to add these three missing pieces? And I think you'll find out that as we've actually worked on the development, that they're not as complicated as you might think. And that's if we have time, we'll get into why that would be and how the way the mind works. It has a huge scale, but can't have a lot of intricately defined algorithms because there just isn't enough DNA to support it. And lastly, we'll talk about the future impacts. What will it be like when you have a computer that has common sense? Just talking a little bit about myself, for those of you who don't know, I've spent my entire career here in software, a little bit in hardware. I have an electrical engineering degree, and one of the things that really got me going in this direction is I got a contract to develop a whole slew of neurological test instruments. So if you have a head injury or carpal tunnel syndrome or one of these neurological problems, there's a good chance you'll be hooked to my software. And based on that, I wrote the brain simulator, which simulates a simple model of biological neurons. And from that, you can glean what it is that neurons are good at and what it is that they're not very good at. And one of the things that they're not very good at are pretty much all of the algorithms that are used in today's artificial intelligence. And we can delve into that at great length if you like. I'd like to also just begin using a new term, artificial common sense, or ACS, because it makes the slides more compact so we can move further a little faster. So step one, defining common sense. This is a definition that I took from this book by Brockman and Levesque, common sense is the ability to make effective use of ordinary, everyday, experiential knowledge in achieving ordinary, everyday practical goals. And there are some implications. I should point out that in the book, there are 3 or 4 other definitions that focus on different aspects, but this is the one I liked. The human mind is really good at common sense. And the reason that it's good at that is if you think about human evolution and, cavemen and et cetera, the brain evolved for the purpose of things that you need in order to survive, and things like finding your way or understanding what's dangerous and what's edible, things like that. And it can be coerced into playing chess, but that is not its natural intent. So as we move forward and look at what common sense is, there are a whole lot of different levels of common sense. And it is my contention that if you want a computer with adult level common sense, which I think we do, you have to do child level common sense first, because everything builds on the step below it. And we think about some of the things that children know that AI is really lacking in is things like simple things like objects exist and they persist in a 3-dimensional environment. The idea of cause and effect, you take an action and the environment gives you some sort of reaction. You understand the passage of time. Young children understand all of this, and yet none of our AIs do. And this leads me to paraphrase Moravec's paradox very loosely, in that hard problems are easy and easy problems are hard. And I was talking to William about this before we got started, which is largely we misperceive what is easy and what is hard. And the things that young children do are really hard intelligence problems. And so I start by looking at, well, what does a child do? And I've found this video clip of a little girl stacking blocks, and we could spend the rest of the hour just itemizing the things that she knows to be able to do this. Obviously, she understands simple physics, and here she's going to reach into the box because she remembers that there were objects in the box that she may want to use, that even though when she can't see them. And obviously in her mind, she is picturing a goal or objective of, she wants to stack the blocks. And when she achieves that objective, she is obviously just thrilled. And as I say, in vision or balance or all kinds of things, we could spend the rest of the hour discussing all of the things that young children know. But now we're going to take a sharp left turn to be able to say, well, if AI doesn't do this, why is that, and why is AI the way it is? And I want to bring up the 2 most prominent areas of AI that are in current usage today. The first being the artificial neural network, which is really good at pattern recognition. We can look at this as a powerful statistical method that recognizes patterns in data. And the way you do this, most of you guys understand that you have this vast library of training data, and you put that into the network, and the network adjusts all of the weights between all of the hidden layers. And then when you subsequently give it new data, the system can identify what the pattern is. And typically you have a number of output categories, and the output will categorize the input to the best of its ability based on the information that you've given it. And then the alternative that we've gotten a lot of use out of recently is generative AI, of which the example is ChatGPT. We can think of this as the greatest autocomplete system ever created. And of course, with every new iteration, it gets even better. But it is a neural network that recognizes patterns, but instead of returning what is the category, it returns what is likely to come next. And you can easily imagine that if you give it a simple autocomplete, as you give it a 3-word sentence, the boy fell, and then you have a choice of what are the words like fell down, fell in the mud, fell. But so you've got a what comes next system, and obviously the longer the input stream is, the more variability you can have in the output stream. So if I give it 1,000 words of input and say I want a 1,000-word term paper based on this something or other, the system can give a very, very good result. And the more data you give it, the better it gives the appearance of thinking. And with today's ChatGPT, there are likely trillions of items of information, of training data embedded into the neural network. And so the neural network can really do surprising things. But on the other hand, there's the idea of hallucination, which is the system simply appears to make stuff up. And you run into this typically if you give it to the request to do a term paper and you want references in your term paper, and largely all of the references are going to be complete fiction, but they will have the correct form. They will have the right sorts of words that you would expect to find in the references. But the key to understanding is that the system isn't hallucinating, because the ChatGPT system makes up everything. And it has no understanding whatsoever of what any of these words mean, except in relationship to other words. And so it has no concept of this is true information and this is false information, even based on the idea that the information that it's based on comes out of the internet, which contains a lot of false stuff, but it contains overwhelmingly true stuff, especially in the common sense areas. But so you're overwhelmingly going to get correct information out of it. And that gives you the false sense that it's actually thinking or doing something intelligent, when in fact it is simply giving you the most likely stream of words that came out based on your input request. So the neural networks and the GPT system work in ways nothing like the way your brain works. And I've done a 10 article series on this and a number of videos that not only explain how your brain works differently, but that it would be impossible and impossibly slow to do neural network sorts of things in your brain, with the small exception of certain feed-forward mechanisms. But there are so many problems inherent in neurons, largely because neurons are so slow that if you try to do anything complex in neurons and begin to use them as switching devices, you very quickly run into the time constraints, where neurons are so slow that you'll suddenly take seconds or minutes or hours to do something that you can do in a computerized neural networks in a few milliseconds. So I want to talk about what are the aspects of understanding and what can your mind do that AI can't. And I pulled together, here's where we get to the 3 items that I think are of paramount importance to adding common sense to AI. And my working hypothesis is if we add these 3 things, then we will actually have a common sense AI, but it's a good working hypothesis. But I am sure that if we add these things, we'll end up with a system that's better than what we have today. So number 1 on my list, that we are good at inferring and remembering rules more than we remember data. And as an example, I can tell you that Spot and Rover and Rex are all dogs, and I can give you certain examples of dogs having certain attributes, and your mind automatically moves all of these attributes upwards to the dog. So you don't have to have storage for every attribute of everything you know, because your mind builds a hierarchy and it can inherit attributes from other things. So when you remember a face, for example, you don't have to remember 2 eyes, a nose, and a mouth. You only have to remember the things that make that face unique. And when you think about only usually remembering the exceptions and what makes something unique, you've got a huge data compression mechanism going on. And so all you have to do is remember the rules and the exceptions. And if you do that, of course, then you can spell almost every word in the English language. If you remember all the exceptions, then you can spell them all. But I asked ChatGPT to give me an image that illustrates this knowledge, and an image illustrates, I think it's an outstanding image, but of course, now it has this M in it instead of things, it has thims. And this illustrates that the GPT is good at understanding the image, and the M looks a lot like an N. And so the system builds this image, and it sort of is right, but it doesn't really understand, and it doesn't really relate the words to the image very well at all. And of course, you can tell that the evolution of these two systems, that the DALL-E does images and the GPT does text, and as these were coming from different directions, and so they aren't married together very well. Next on my list of things we need is multisensory experience. You understand things because you've seen them and heard them and tasted them and touched them and felt them. And so when you think of dog, you think not only of what it looks like or what the words are that describe it, but if it's wet, you know what it smells like, and you know what its fur feels like, and you know how the fur of a dog feels different from the fur of the cat. And these multisensory experiences give you a vast breadth of understanding that doesn't exist if you only know the words or only know the images. And what this says to me is that common sense has to be based on a robotic kind of a system, because the robotic system can go out into the world and it can experience 3 dimensions. It can understand what a point of view is and how data all appears to shift as you move through the environment, even though when the objects themselves aren't moving. Once you have developed a common sense system, you don't need the robot so much anymore, because in the same way you can cover your eyes and still understand what vision is and color and shape and visual items and cause and effect and all of these 3-dimensionality things that you learned because you've had this multisensory experience, you don't need it so much once you've done this learning. And so what I envision is a system with common sense that does what you think GPT should. If GPT did what its ideal aspect was. Another thing that humans were really good at that we saw before is, is planning. And I'm not talking about complex plans, because humans are really not very good at planning, which is why we do all our planning on a pencil and paper or a PowerPoint or something. But the simple thing that the girl does of imagining an action, understanding whether or not that is achieving her current goal, and then performing that action. So it's a very simple process, but it requires that you have a mental model of the world, so that the way we can think of the way your mind works as being centered on a mental model, that all of your sensory input is being piled into this mental model of your surroundings. And then you can imagine things within that mental model to plan, and that mental model is continuously updated as you learn more data. And I'll talk just a little bit more about that in a couple of slides. These things may seem complicated, but I see them as happening within the next 5 years because of the progress we've already made. So we have the Universal Knowledge Store, the UKS, that can infer and remember data, and we're working on that, and it can handle the rules and it can handle the exceptions. So the question is now how, and we have robots, and the question, these pods go around and experience the universe, the environment, and the question is, well, how successfully can we tie the multisensory experience into the mental model? And there's some work to be done there. And then we have a system that can do planning in a very limited way. And so I see these things that we have essentially prototyped. And if you have a good prototype of something, you can easily see a pathway to making it work in a real world in a 5-year kind of a time frame. And that's why I see common sense is happening in that time frame, rather than the 50 years or the never time frame that other people see. But a key is that it requires an entirely different approach to AI than is the current mainstream today. When we build this sort of system, the question is, well, how human-like is it going to be, and how much like a human mind is it going? What behaviors will it have, and what? We can look at the human mind as having a bunch of behaviors, and we can implement these, and it also has an internal sensation or a set of feelings, and we don't really understand how these work at all. And we can say, though, that when you see the orange or the blue on this slide, in your mind, you don't think about orange or blue. You have a specific sensation that's associated with it. And we assume that you and I have the same internal sensation. And so you see orange the same way I do. But if within your mind, orange and blue were reversed, since orange and blue are just neuron firings, and if they were reversed from what I perceive, we'd have no way of knowing. And so when we ask, well, will a common sense computer have internal sensations? Well, we don't really have any way of knowing that at this time either. But I've said in other presentations that if you are addressing a machine and it may or may not have an internal sensation, but it acts like it does, and you're reasonably confident that 10 years from now, that machine is going to be much smarter and more capable than it is today, it might be a good idea to give the machine the benefit of the doubt. So let's talk about the impact of adding these features to AI. ACS will necessarily be different from human common sense because all of these internal sensations must be different. We humans have sensations based on what we needed to survive. Are we well fed? Are we warm enough? Are we safe? Are we happy? Essentially, all of the emotions and feelings base upon our goals on survival in a wild environment. And none of these sensations make any sense for a robot. So these human mind sensations and goals have all evolved over thousands of years in the wild. ACS is going to be planned over a very small number of years by humans who are likely to get it wrong. So rather than being concerned about the problem of the future of ACS taking over the world, I'm concerned about the people that own them. And if we set up a set of goals for our ACS that it's going to be truthful and helpful, that's an entirely different ACS than if we set up an ACS to maximize profits. Because when we think about science fiction, there's always this conflict between humans and robots. And it doesn't have to be that way. It's that way because it makes a good story and the humans read the stories. So you don't need to be in conflict, because mostly when I'm in conflict with you, it's because you have stuff and I want to take it, or vice versa. And in an ACS, from an ACS's perspective, the humans don't have a lot that the ACSs want. And so you have some crazy stuff like in the Matrix where we use humans and batteries. Of course, that's nonsense because they had to make up something that the Matrix and the AIs would want to have that the humans have in order to build the conflict that's necessary to the story. What about jobs? Every presentation like this has to talk about jobs, so I included a picture. And the nut of it is technology always displaces jobs, and we just have to get over it. And if we planned for people to change jobs and change professions on a more regular basis, we wouldn't be so worried about it. But we still are working under the 100 years ago concept that you get a profession and you're going to live with that profession and do the same thing for the rest of your life. And that simply is not the case. And we need to get over that and move on. I want to just mention AI energy requirements because today these AI like ChatGPT runs on supercomputers and it requires megawatts of energy and takes months of supercomputer time in order to be trained. And this is entirely unnecessary. And well, it's necessary for the way it works today, but I, in my mind, can do a lot of things that AI cannot do, and my mind works inside my head with 12 watts of energy and takes up only this space. So to me, that's a proof positive that you can create common sense in some sort of other medium that doesn't require so much energy, and that the AI energy requirements today is because of the way they're built, not because of the outcomes they produce. So just summarizing, ACS will make computers better. Because of that, I see that ACS is inevitable and not very far in the future. Once you have an ACS, the march of technology will make subsequent superhuman ACSs rather in only a decade thereafter, for example. Robots are not as necessary as they are depicted in science fiction, but we shouldn't expect the ACS to be the same as a human in terms of the way it reacts and the way it feels. It's always going to be different because its sensory, its sensations, and its training have all been different. I think the danger that's overstated, but either way, the impact will be huge. Okay, now I'd like to move on to the fun part of this conversation where I get to hear back from you with questions and things. So who wants to lead off?
Charles, so I've sent you 2 long emails about this video. I got your email earlier today about, thinking about the larger consequences. And then I've just listened to this other presentation. So I took notes, and the first and we talk a little bit about organizing in the beginning, right? How do you, before you started. The first organizing principle I have is stating the goal of what I think you're really after in this video. And I think that goal is convince viewers that investing in ACS is well worth it.
Yeah.
Okay. So that's what I think your real thrust is here. And then I have 10 steps, all in order, that I can send you all this. It's all written down. That that can get a person to be convinced. It's like you're making an investor pitch, really, right? And so just to give you a flavor, the first one is, how can it help humanity to give computers common sense? And when I was writing that down, I said to myself, forget about AI, forget about, fancy tech and all that stuff. How does it help humanity? Get us to, my first cut when I'm listening to an investor pitch is if the proponent is correct, if they're honest and correct, will it really matter? And then I have all these, another 9 steps about how you can convince a person that this is worth investing in. I'll send it to you, but it's ordered. It's carefully ordered around this goal and flowing from me, how can it help? And how hard would it be? Is it worth the ROI? And only then do we start into what is common sense. People already have some notion of it, but they don't really know. Only then do they know what it is. And then how is ACS different than natural CS? How can we do it? And convince me that it can be done. A lot of your stuff was sort of related to that, but I have a little different approach to how it can be done. And this is the way I think. What would it take to convince me that you're right? I mean, I think you're right, but if I didn't know you and if I didn't know what I'd known in my career, what would it take?
Well, what would you see would be the principal benefit to humanity from a common sense machine?
Well, then we just have to list humanity's problems. We got climate change, we've got humanity, we've got authoritarians, we got war, we've got disease, all of those things. And we're in a lot of things we're kind of stuck. I mean, we're advancing technically, but if our technology is so great, why do we have a housing crisis? What drives me nuts? The cost of building a house per square foot is going up, not down. We have cell phones, we have computers, we've got some AI, we've got new kinds of tools, we got laser levelers, we've got planning tools. Why is the cost of housing going up? I know some answers to that, but just that, housing is the #1 cost for a normal family. Like, no, it beats everything else, right? Shockingly, transportation is number 2.
So you would see the common sense system as something that we might actually listen to.
That sounds like an unlikely scenario.
Well,
one of my thoughts about common sense is that it's very siloed, and it's so dependent upon your worldview that some people think that blowing themselves up with explosives to kill the bad guys is a good thing. That has always struck me as rather far-fetched, but somehow in their heads they've resolved that conflict. So if you took your statement of, if it sounds too good to be true, it's not true, when does that even apply? And if it's in the stock market and you had a computer that could actually answer that question and keep you away from the Bernie Madoffs, that would be pretty useful to some people. But it doesn't seem like it. I don't know. It's whether that qualifies as common sense under your definition is a little. I'm just asking.
I would also state that certain common sense is a little bit different depending on each person's brain. So, for instance, people with Asperger's syndrome have been described as little professors, since from at a young age they're more, or at least some of them have abilities that are only seen within adults with normal brains. And they've been described as more logical, so to speak. So I guess what kind of brain are we modeling this off of?
Yeah, well, I happen to be saying, well, what do we see that most people do? And are those situations that we can model and replicate? And then after we've modeled and replicated them, and then we ask the question, well, what benefit do you get from that? And I bring up the problem that there's this huge opportunity for benefit, but we aren't listening to the people that understand the problems and to their solutions at the moment. And if we get the same solution suggested out of a machine, are we any more likely to pay attention?
Well, an expert is somebody from 500 miles away. I do have a comment on your efficiency metrics.
Yeah.
Almost every sensory system in our body has a neural network-like mechanism. So the eyes have all sorts of layers of pattern recognition built into the eyeball before they bother to send the information. The ears do exactly the same thing. Your reflexes are set up so that a whole bunch of the information is pre-processed before it goes up to your head. And so those are all kind of GPU-like functions that keep your very, very slow CPU from having to deal with, you know, the amount of data that's presented. So just a thought, I agree that brains are very slow, but they have some GPU-like capability helping them out.
Well, they certainly have a lot of parallelism. And one of the things that I did as an undergraduate is telephone systems were changing over from relays to transistors. And so there were a lot of telephone relays available, and we built a CPU out of telephone relays. And these telephone relays would switch in about 12 milliseconds. And this gives an entirely different perspective on what switching circuitry is about. And if you wanted to build circuitry out of neurons that requires that switch in perhaps 1 millisecond, well, that's a whole lot closer to it being a telephone relay than it is to being a transistor. And it puts a whole lot of constraints on what you can do. And I'm a little reluctant to say it's a neural network, because neural network these days usually means training via backpropagation. Well, in the mind, you can easily have lots of different feed-forward neural networks. And I'm thinking that as the brain simulator evolves, that we're going to find mostly feed-forward neural networks. But the backpropagation algorithm is as a learning mechanism is a complete impossibility, because it's just too cumbersome and slow to be practical in a mind built out of such slow components.
So would you like a different opinion?
Sure.
I agree with most of what you say, but since these are questions that are, you know, enormous questions to be even asking, when you're learning language in those first 2 years of life, one of the questions is, what are you learning? And I think the answer is that your inner ear is actually learning to turn acoustic signals into quantum pieces of information, i.e. the sounds of things. And your brain is then learning to take those sounds of things and turn them into words or into concepts. And so people who grow up in a different culture or a different language basis can't even hear the sounds that we make. They can't even recognize them. They don't have any mechanism to do that. It's a real challenge. So it's actually easier to learn to read Chinese than to hear and understand Chinese, because your eyes can do a very different translation. I don't know, does that mean that the training process during those 2 years is very intensive and specific and Maybe we already have this training process in place.
Clearly, there's a training process. And the question is, well, how does that work based on these crazy slow components? And my suspicion is that the first thing initially you remember everything, and then you discard the stuff that doesn't get reinforced. That's only a speculation, but it's an entirely different mechanism than backpropagation.
So I guess, are we planning on adding stages of learning to our system? Because I know, for example, kids are better at learning languages, and then as we grow up, our brain kind of prioritizes learning different kinds of information. How it becomes harder to learn languages as you grow up and that sort of thing.
That's true, and I'm not sure whether we have to include that in the system, and that's a real question. We may find that as you, for example, are learning all of the acoustic learning that you need to do to understand language, as John brought up, that eventually that fills up and you move on to learning different things rather than having to plan ahead and say that, well, we're going to make a system that does this here and this here and that there, that maybe it just will all flow naturally from what you encounter in your environment.
Yeah, I was just thinking maybe the brain prioritizes things in stages to deal with the performance costs of it.
Sure, and maybe it learns the things that it learns based on the hierarchy of how far things are from the basic sensory input. That when you're learning vision, you first have to learn about what is an area and what's a boundary and what's a corner and what's a curve, and from that you can build more complicated things of, this is a square, and this is a square in a three-dimensional environment that's on an angle, and then you can get to be 5 years old, and you've got with those components already learned, and then you can learn how to read, and you can learn all of these little symbols. But that's entirely speculation. I don't have any basis for that information. I did want to add, by the way, that as we are writing all of these complicated algorithms, the amount of information contained in your DNA isn't really very good, isn't very great from a computing point of view. And the amount of that DNA that is dedicated to fabricating a brain is unknown, but clearly smaller. And the amount that is dedicated to making a human brain as opposed to some other kind of a brain is minuscule. And so if we start off with the idea that we're going to write, gigabytes of source code in order to create some algorithms that do something, we've clearly gone way beyond how the brain can possibly be developed, that the brain has to be developed out of repeating patterns and then develops itself based on the input that it gets from the environment, rather than being entirely mapped out with all of its capabilities to start with, because there just isn't enough DNA to support all of these capabilities. So we have to figure out, well, what are the basic rules of replication that we might be able to have? And that's what I've put into the UKS and the sensory system, that you assume that you have a sensory system of various robotic sensors driving into a UKS. and the UKS isn't particularly complicated, but as we move on, we keep adding more Christmas tree, more and more stuff onto it that makes it more complicated. But as I'm working on the vision system, and I've got this algorithm that prioritizes line discovery and stuff like that, and I know that your vision system can't possibly work that way because it's just too complicated for words. And I would say that I'm doing it that way because it's fast. And a lot of professors and graduate students have come up with these really cool algorithms. And if I just employ those algorithms, then I get some output. Whereas if I just fumble around and say, well, it's going to be, let's see if we can figure it out, I'm going to be to the next 5 years before I can recognize what a square is.
Great question. I ride to work on my bike, and every morning the ducks are out there eating little bits of gravel from the side of the road. And it just makes me wonder, where does the understanding that they need to be eating gravel to digest their food, where does it live? Is it DNA? Is it,
yeah.
Answer that question and we will know what common sense consists of.
Yeah, one of the things, by the way, that I didn't include in the presentation, because you guys who are more technical will understand it pretty well, is that when you have this internal mental model, you're getting information into the mental model and you're remembering stuff, and then you're recalling data from your memory and pouring it back into the mental model. And so you have this feedback loop. And I've talked to John about this, that whenever you have these circular systems within a brain or within any electronic system, you risk having oscillations. That you can, whenever you have these circular systems, you can have an oscillation. And one of the things, and as I say, I think the mental model is a necessary precursor to consciousness and the internal sensation of being a human. And so you have to balance the kind of feedback that happens in your brain versus the advantage that it gives you, because we're taking an awful risk. And one of the things, how this risk manifests itself, is that we can see that people do have brain oscillations, and we call it epilepsy, and we would prefer not to have that. But as a secondary corollary, we could say that animals and objects that can never have seizures probably also don't have reflective internal thought and internal sensations, because the same process that gives you these also gives you the risk of the oscillation. So I would, contrary to some of the philosophers, I would say that an ant has no internal sensation of being an ant. Ant is an automaton.
Yeah.
Somewhere between humans and ants, there's this scale of magnitude of internal sensation, but it's also not a all or nothing proposition. So if we were to say that at one end of the spectrum, we've got humans that have tremendous amounts of internal sensation, and we have no idea if gorillas and dolphins have a similar magnitude of internal sensation. But it's likely that mice have less, simply because they have a lot less hardware to be able to have that internal sensation.
Charles, some of what we're talking about is bootstrapping systems, and
yeah.
one of the comments in your video, and you repeated it here, was that after we get a basic understanding of three-dimensional space and everything, we need robots less. We need, these machines to go out in the world sense, because we've got the mental model to work.
Yeah.
So one of the things I've done since we've talked is talk to Henry, who you know.
Really?
about what you're up to, and specifically the notion of being able to use ChatGPT to acquire common sense with proper prompt engineering. Okay. And so he said to me that, well, you can do that, but it's going to be about 80% correct or something, and it's hard to, tweak it out, right? But we can get about 90% correct by building off of ConceptNet. And there's a group at USC in LA that has built on top of ConceptNet and integrated in WordNet and a whole bunch of other smaller common sense databases. I can send you all this stuff. But the reason I'm bringing this up is maybe we can bootstrap the system faster by snarfing down this large knowledge base of common sense stuff, and then have a good base that we won't have to do the bootstrapping so much. We'll be starting off theoretically, the dream would be we'll be starting off at that level that you said, oh, we no longer need robots so much. Now, I like robots for other reasons than for acquiring things, although I do think it's really great for any intelligent system to be able to conduct experiments on its own and see stuff. But what if we get all that information kind of for free? And what I mean by getting it, I mean in a UKS-like format, in a really structured format that's much better than the LLMs or the neural nets are going to give us, right? And then use that as the platform to then build off of and get a kind of a jump start.
The problem that we need to solve is that these systems that are based on language have always given me a lot of trouble in their ambiguity. And I have some ideas on how that would work, but how we might solve this problem, but I haven't gone down the road very far. And the problem that we run into, and we get this out of ChatGPT, but I also found it in ConceptNet and some other data sources, is you say Fido is a dog, okay, dog is an animal, or a dog is a pet. And a pet is a good friend, and a good friend is a person, and a person has 2 legs, and now Fido has 2 legs.
Yeah.
So, and the problem is that because and that isn't even an error of the ambiguity of language.
Yeah.
It's the ambiguity of thought that a good friend has multiple concepts associated with it.
Yes.
And before we pull in piles more data out of GPT, or any other source, we have to figure out how we're going to get the ambiguity of thought resolved. And I have some ideas of things to try, but I don't have a real solution. But the problem, I mean, I illustrate this problem with you don't want Fido to have 2 legs because of this chain of information.
Doing long chains of inferencing, often, you get 10% worse at each inference level. And then by the time you're out 5 or 6, it's garbage.
Exactly. And so one of the things that might solve that problem is if you know that Fido is a dog and dogs have 4 legs, of course, that is filtered out because it's an exception to the idea that people have 2 legs, because you'll encounter that information further up the inference chain. But but it doesn't always work that way.
Charles, the problem that you brought up is exactly the problem that I
Yitta, your
struggle.
mic is terrible.
Oh,
It's really low.
is this, how about now? Is it okay?
No, no. I don't know what to say. But Charles, normally the way people deal with one word having two meanings is in context. So we have context. You know, psych had these micro worlds, and that's one attempt at solving that. But do you have some other ideas about solving that core problem? Because I agree with you, it's a really important one.
My idea is that we have an area of the UKS which is abstract thought. And when you have abstract thought, it is unambiguous that when I suggest to you to think of a table, you might have a table of rows and columns, or you might have a table with 4 legs, but within your mind, you've thought of one of those tables, and you, in your mind, have an unambiguous solution. And so if we assume that in your mental model and a group of abstract thoughts, all of those thoughts are unambiguous.
Okay.
Now we have a section of language, and you have a many-to-many comparison, and you can add many relationships between the language words and the abstract thoughts, and that's where the context gets provided on to make the language work.
So we've got a table of numbers and a table of furniture in our sort of real world side, and then we've got the abstract table of furniture and the abstract table of numbers. They're totally separate. I mean, they might have the word associated, but that's just kind of a mistake. Okay, now, given that situation, how does this help us?
Now if you see the table, if you see it visually, clearly there's no relationship between the two. So you know unambiguously what kind of table you're looking at.
Okay.
But they both have the relationship to the word table, so you can say that's a table regardless of what it was.
The word is almost superficial here. Would you say that's true? And don't base your reasoning based on words, because they have multiple definitions and you're just going to get screwed up. Yes,
absolutely. I would contend that if you have a system, any AI system based on words is doomed to ambiguity.
Okay, good. This is good. I like this stuff.
And so you have to have an abstract underlying form that is absolutely unambiguous to you.
Yes, but then when somebody says the word table to you, can you learn something? Oh, table's made out of wood or something. You're usually in a context.
Yes.
Right. And so if you know the context that you're in, then you can do the disambiguation.
Yeah.
And now we get into the problem of what is a context? How do we define them? Are contexts sort of these Gaussian shaped things that bleed into each other? You know, maybe context becomes the central thing to work on here.
And we may find that it's actually really easy, that if I'm talking about numbers, you're always going to think of the numeric table. And if I'm talking about furniture, you're always going to think of the legged table. And
how many contexts do we need? Do we need 100 or 1,000 or 1,000,000 or, you know?
I think that like a little like GPT, it's just relationships that it's not a thing. It's just that if I use this word near that word, or I introduce this concept near that concept, they have to work together, and it's not anything that you ever have to specify. But as I say, this is all half-baked. It's all as I say, this is not ready to be turned into software, but I have an idea of a direction to go. So what were you going to say, John? And we also got a comment from Yida that I want to go read.
Yeah, well, I have a problem to solve, and this is kind of circumnavigating the problem. One of the contexts we deal with is reading EEG records.
Mm-hmm.
And Mayo Clinic and Stanford and UCSD all describe the same phenomena using different terms. As a result, even though you have these EEG reports, it's difficult to pull them all together and run them into some sort of machine learning algorithm, because the machine doesn't know how things are the same and what things are different. So the solution to that has, of course, there are many, many solutions now, is that they come up with a scoring system where a concept is enumerated. So it's got a random number associated with it. And we don't care what you call it, as long as that enumeration actually matches whatever shows up on this wiggly line on the screen. So that was their solution in reading.
Well,
context.
they had the advantage. Essentially, what they did there was they changed the language.
Yes, and they have a very, very tightly circumscribed context. But at least they, in theory, only have one. By the way, this hasn't caught on. So Mayo Clinic and Stanford still, they have the way to describe EEG, as you might expect.
Mm-hmm.
Anyway, we're trying to help resolve that problem.
But to some extent, it's exactly the same problem of you have a user who speaks English and a user who speaks French. And you have an underlying concept that you want to describe, and you know what that underlying concept is, and now you want to describe it in one language or the other.
Yes,
except your two languages are Stanford and Mayo.
Well, and the language, of course, we pick is essentially a GUID.
Mm-hmm.
We simply assign this random term that has no real meaning to a specific concept. And then everybody is supposed to say, well, I'm going to call it a seizure and you'll call it an epileptic discharge. But if we look at it, it's supposedly the same thing.
Mm-hmm. Yeah.
Anyway, help me solve this problem and I will continue to watch your lecture series. This is it's very inspiring.
Well, one can easily imagine that if I have an area of the UKS that is words and an area of the UKS that is concepts, that I can create relationships between the words and concepts any way I want, and could have multiple collections of words in different languages and then select a language and etc. So one could easily imagine that there is a structure of how to put that together. And I had a brief conversation with William that maybe he could write this, but it occurs to me that we're going to have to try some things out first. That we'll build ourselves a little experiment and see if we can make anything work. What did you say here? Yes, it's a good counter example.
How's my audio now? If not good, I'll just stick to typing.
Oh, you're speaking fine now.
Oh, okay.
You're fixed, whatever it was.
I think there was. Yeah.
Anyway. Yes, that one of the things that I learned getting data out of GPT is that once you decided that a duck was an animal, it was no longer an action. That once it starts giving you an answer in one context, that it will be consistent and continuing to live with that context And so it's in that respect, I was getting much better data out of it than I was getting out of ConceptNet. But now that we've built up the system out of GPT, we might go back to ConceptNet. And for those of you who don't know, ConceptNet was a knowledge base that was built open source, and that is, anybody could log in and add knowledge to it any way they wanted, and it got a lot of data, but I think it has 10 million entries on that order of magnitude. But the neat thing about it is you can download the whole thing and put it in RAM and search it in a flash. And I've done that. And I did write a really crude system for translating it all into UKS. And a problem that we also that I also have to overcome is that if you have these erroneous multiple references, the way the search works is it kind of broadens out, and I haven't written very good limits on it yet, so it takes a huge amount of time to come back. But that, I don't see that as a big deal as soon as I fix it. In a nutshell, you should be able to throw anything you want into the UKS, and the searches should still run quickly. I shouldn't constrain the data to be incorrect in order for the system to work, because the data is never going to be correct. Okay, well, thank you so much, all of you. I sure appreciate your time and your comments, and we'll be in touch. Thank you.
Thank you.